All right, okay, welcome back. Okay, so I guess before the break, I mentioned that I want you to maybe try the first shot on the classification, but with 4 attributes instead of 2, okay? The only thing that you need to do is just change one thing, one line, and the rest the same. See how powerful this is? When you use Python and you use it in the right way, you normally don't have to change much in order to change your model. Let me show you. Okay. This is the one that I wrote, right? And what I want to do is I want to select my X to be 4 columns, right? Remember that this process, you load in all the data. You have four attributes, right? But then when you were kind of like extracting it out, it's I only choose the last 2 columns from my X, right? All you need to do is just change this number to 0. That's it. And rerun everything. And now you are running the model with 4 columns. Okay, so let's do just that. See, 4, right? But the rest is the same, right? Because like the model is supporting multi-dimensional vectors anyway. So whether you have 2 or 4, it doesn't care. It can support everything, right? Even the training and predicting, right? Everything's the same, right? I mean, I guess behind the scene is different, but your procedure is the same. And even your accuracy score, like now, is actually lower, right? So, but one thing is that this plot doesn't work because this plot is only expecting that you have 2 columns for X. Because if you have 4 columns, I don't know how to plot 4-dimensional data. It's too hard to do visualization in 4 dimensions. That's why I don't support it. So it's okay for this to have error. But again, you can see that if you have 4 or more data, if you want your accuracy to be higher, you probably need to adjust your parameter. Like the same parameter that works for 2 columns probably doesn't work with the 4 columns. So I guess if you want to try further, you can adjust things now. For example, you can I guess the thing that you want to try is your learning rate to see if that's changing or not, right? So you can do, I don't know, 0.01. It's actually even worse, right? Maybe you can change your iteration rates, things like that, to be maybe 0.1. I'm not sure. Let's see. So I think I'm going to comment this one so that maybe I can, it doesn't give me error, right? So as you can see that when you have 4 columns for X, then you can no longer visualize like a decision surface nicely. So all you have is pretty much just your model accuracy. And also there are other matrices that we can learn, that we're going to use after the midterm. So that's something that you might need to experiment with, right? And as you can see that sometimes increasing more columns might not help you because sometimes it's actually more confusing to the model. So in this case, maybe only use 2 columns might be enough. That's the job for the practitioner to determine whether that column is actually more useful or not. That's another topic on its own. So, it's called the dimensional reduction. So sometimes you might want to get rid of the columns that's actually problematic too. Okay? But we're going to move on to explore other models because actually changing the model, it's actually changing, it's a more drastic change and probably will give you a better way to classify your stuff. Okay? So let's us quickly go through a bunch of a common model in machine learning. Which is going to be another lecture called the classification model. So another file in your link. Okay, so this one right here. Okay, so today we're going to cover 5 more models. And you can see that actually your process is the same. You only need to change a couple things. and you can change a model very, very quickly. Okay, so that's the power of writing code, is that it's very, very easy to change. Okay, the first one is called logistic regressions. Okay, if you are going to use a linear model and you don't want to use the neural network, I think this one is the best one to use. Okay, even though it has the word regression in it, this one is not doing what you think it does. It doesn't predict value. It's actually predicting class. Okay, so it's for classification. Okay, even though the name is called regression. I think after midterm we're gonna learn about the regression.
What's like the difference between classification and
Okay, let me go back to this slide just to make sure. Okay, I'm gonna go back to the first one. Not this one. Where is it? This one right here. So, what we are doing right now is called supervised learning. The fact that we give the model the training data, that's called supervised learning. But there are two class of model. The first one is classification. This model will give you a class, 0, 1, or 2, or 3, or whatever. But regression, it's a model that gives you continuous value. Like if you want to predict the price of something, like your stock price, you want to use regression model because it gives you the actual price of your stock in the future. So that's called regression model. So when we use the term regression, people usually think about things that output the values instead of class. But the model called logistic regression, it is a classification model because logistic regression gives you class. So this actually is a question from the committee that I was in at one point, and the student cannot answer. The committee was asking like, why are you using logistic regression for your classification tasks? And the student cannot answer. And I was like, man, you could have known from these slides. Okay, anyway, the reason that I say that the logistic regression is probably your best model to use for the linear model, not perceptron, is that because logistic regression gives you probability. That is extremely useful in so many things. Probability ties into statistics right away. And you can use that for any statistical analysis afterwards. So if you want to say p-value, confidence interval, if you want to get anything like that, you need probability. And the only model in machine learning that I want to teach you in this class that gives you the real probability is logistic regression. So this one ties into statistics really nicely. And I even use this in my production because in my application in production because of the fact that I want probability from my model. This is so useful. I cannot stress this enough. So, but the only thing is that it's a linear model. So if your linear model is not good enough, so then that's okay. But linear model, logistic regression is the way to go, man. I'm telling you. Okay, that's it. All right? We're going to use them. So I'm actually skipping a lot of things. But if you want the full details of what it is, you can go to the detail folder. And I have the actual full, full description of the model itself. For example, I have all the equations and all the derivation of all the model, but we don't have time in here, so that's why I'm skipping all of those. If you're interested, come talk to me. I can explain more. I actually have all of the explanation, but it's in Thai. So sorry guys, I don't have it in English. I taught this one before, but then I guess later on I decided to cut all this detail because I want to cover more stuff in the future. So, but then I guess my first rendition of this course, I actually go through all this detail. But it turns out that like by the time it's final week, I only teach like up to just machine learning in it's covering things not wide enough, so I decided to cut out all the details. But
Do we also have like unsupervised learning? Like I'm using DE scan and payments.
yeah, I want to cover that. That's why I'm skipping all this detail. Because I know you want it, and that's something that I've been looking at nowadays. I use unsupervised learning more and more, so I want to at least maybe have a topic on that too. So I do. So you have my promise. Yeah. But again, so I'm just gonna tell you what it is, and I'm gonna tell you the parameter to choose, and we're gonna go right into coding. So that's gonna be the process from now on. So in the logistic regression, the things that you want to use is C value, okay? So the C value, the official name is called the regularization strength, but it's an inverse of it, okay? So this name, you can think about is control. It's kind of like a control of the weight value, okay? So if the regularization strength is high, I mean, oh, sorry, not control, but suppression. Suppression would be the right word. Okay, my handwriting is too bad. Okay, let me write again. So what I mean by suppression, right? Okay. Okay. So that's what the Z means. But the Z is actually the inverse of that strength, okay? So the regularization strength is suppression of weight, right? Remember in the linear equation, there's always the slope, like the weight, right? This W, right? If you don't suppress it, this W can become large. So maybe if high suppression, right? High suppression means small C. Because C is the inverse of the strength. So if the strength is the suppression, high suppression is smaller C, right? So that means that the weight is small weight. Okay? And actually I'm writing here, it's actually in here, right? Smaller C means smaller weight because of high suppression, right? And if you don't suppress anything, it's large C. That means you're going to end up with large weights, okay? The reason that you might want to suppress your model is that you want to tame your model so that it doesn't respond too much to noise. Sometimes if your data is noisy, your model will try to fit a lot to the noise, and it's kind of going way back, it's kind of fluctuating the weight too much. So you want to suppress it so that it doesn't care much about the noise. And that's depending on your data. But I guess the trade-off, if you suppress things too much, it can affect the accuracy of the model. Like if you kind of, I guess if you suppress the weights too much, it suppresses the ability for the model to learn too. Okay, so that's the trade-off that you gotta make with the choice of your C parameters, okay? All right, so let's go into our data model and then just try to do the same thing, classification with the iris data sets. Again, I'm going to use only two attributes because I want to visualize the decision surface, okay? And I'm going to use Z, which is ranging from very small. Again, smaller mean high suppression. So this one is making your model cannot do anything much. But then I'm going to let the model do whatever it wants if the C is very high. And you're going to see the difference, okay? All right, so let's do it. Okay, I'm going to come here. And so right now we are going to be in the Logistic Regression folder, Logistic folder. And this is the one that you might want to take a look at when I go through my examples. Okay, so I'm going to create a new file and hopefully it works. If it doesn't work, I need to do more tinkling with it. Okay, so first I'm going to copy the code that loads all this utility functions. Yep, it works. Okay, thank God. Thanks God it's working. Okay, the next thing is that I'm gonna load all the packages that I need, and this is gonna be pretty much the same except for this guy right here. See, it's sklearn, linear model modules, and importing logistic regressions. As you can see that it's a capital L, that means that this one is a class definition. So as you can imagine that all the code that I'm going to do before I load this model is going to be similar, identical to what we do before. Okay? So I'm going to go through them quickly from now on. The first one is that I'm going to load the data set through the load iris function. Run it. Good. Okay? The next step is that I'm going to select the data. Okay? And this one, you can see that if I already know my data, and my data, I don't even need to go to Panda, right? I can just select them right away, okay? Let me show you this if you're still confused what I did here. Iris.data is actually the NumPy array. If you don't believe me, I'm gonna show this. I'm gonna print the type of this data for you. It's actually numpy.nd array. So iris.data, I think on the previous notebook I used a data object. I changed the variable name, right? But iris.data is already numpy array, so we don't need to do anything. We can just use it, right? So if I were to type iris.data, like it's numpy array. So I don't even need to go to Panda data frame. But the only thing that I want is actually I want 2 columns as before. This one for visualizations, right? Again, this data is numpy array can be used as a generator. So that means that I can select something from it. So I can do data. I want to select all the rows, but I want only the last 2 columns, which is column 2 and column 3. Here's the thing. So I think that's what I wrote in my code. Actually, not even what I wrote in my code. In my code, it's even shorter. So I can do all the row, but then column 2 to 3. Sorry, column 3 to 4, not 2 to 3, column 3 to 4. This is column 3 to the 4th column. Okay, so that's it. Same thing, column 3 to 4. Okay, and this one is going to be my X. Okay, so what about my Y? Right, my Y is actually NumPy array before I convert it to Panda data frame. But again, I only need NumPy array. So if I know that my data is already there as a NumPy array, I don't even need to do Panda data frame. So this one makes things quicker. I can do iris.target. Actually, this is already what I want. I don't even need to convert it to anything else. So I can just set this one to my Y. And I already have my X and Y. Okay, so that's the thing that I'm going to use from now on, just to speed things up. Okay, the next thing is the usual data splitting. So X-train and X-test, right? We're going to split things 70 and 30%, test and train data. Let's go. Okay, done. Right? And the next step, as you can see, that's this one is standardization. So that means that we're going to instantiate the class from the class definition. We're going to fit them to the data that we have, which is the training data. Remember, we don't fit the data to the test data. That's the future data. But I can transform all of them because I'm going to use all of this later anyway. So why don't we just do it here? I have my train data and my test data in the transform value. Okay, run it, and we're good to go. Okay, and here is a thing that's specific to the logistic regressions. Okay, it's called the hyperparameters. Okay, so what do I have here? First, I have Z. Okay, Z is the suppression of the weights. Okay, or I guess that's Z value. Okay, Another thing that I haven't told you is a solver, okay? When you solve, okay, this solver is actually doing the same thing as the gradient descent is doing in perceptron, right? It's actually the optimization algorithm when you want to minimize the error with respect to the weight, okay? But what has turned out is that in logistic regressions, even stochastic gradient descent is not good enough. So they come up with a new way of doing the optimization, and it's really complicated. I don't know much about it per se, but there are different solvers even for logistic regression, and the one that kind of standard is this one. It's called LBFGS. Okay, so if you want to learn more of it, you can search Google to see what this optimization algorithm does. In the end, it's like calculus again, but it has more tricks in its sleeve so that to speed things up. Okay. And this one, max iter, it's just saying that if you want to go through the data epoch, don't go through more than 100 times. And that's just, we don't even need this one right now, but I'm just throwing them just to show you that there are many things that we can do for for the hyperparameters. Okay. Okay, so once we have this, we can start constructing the logistic regression model. The way we do that is to use the class definition, logistic regression, that we have loaded, right? And we can start putting things in right away. For example, I can do random states equal 1. I can do verbose equal 1. I can do solver equal solver. I can do C equal C, which is 0.001 at this point. I can do max iter equal max iter. Okay, something like that. Again, you don't even need to use these arguments, right? This one is just a lot, right? If you don't specify anything, it's going to use the default value. So if you want to keep things by default, you don't even have to do anything. You just do the parentheses. And then the training part, I forgot to set this equal to LR. I need to run it once, okay? And then I'm going to do LR. Now, the fitting. The fitting part is, again, the optimization algorithm, finding the weights that optimize, that minimize the error. Okay, so fit. So I'm going to fit with the X-train STD, which is the training data that is standardized. And then Y train, which is the answer. And there you go, you're done. Pretty good, right? Pretty fast. Linear model is usually quite fast, okay? And if you want to do the test data prediction, you can do lr.predict, okay? And give them the X test STD. So now this is kind of like a future data that you will reserve for testing purposes, right? This one is going to equal to Y predict. So that's, I'm going to keep that. And I'm going to feed them into the accuracy score. Okay. I guess in my code, I do have a bit of digging into some of the probability stuff. Okay, so we can do that. So let me just do that. Okay. As I was telling you, the good thing about logistic regression is that it has probability built into the model, okay? So for example, I'm showing you right here that we are predicting 3 classes, right? And actually, you already have the probability of prediction, which means that this one is almost like your confidence of the model. So for example, even though the model is predicting the class number 2, you can see that the model is actually not that confident. How do I know? Because the model probability of class 2 is only 33.6%. It's like it's just above the average, right? If you are not sure about anything, the probability should be like 33%, 33.33%. So that is like, if you are not really sure, just random guess. A random guess would be 100 divided by the class the number of class, so 33.33%. But I guess the model is just a tiny bit more confident than the random guess. So even though you have prediction number 2, it's actually not a very good prediction. I guess the model is actually not that confident. So you should not trust this result that much because it's almost like a random guess. And you see how incredibly useful this is? By knowing this probability, it's so useful because you can interpret the confidence of the model in the probabilistic manner. You don't have this luxury with other model. So that's why this one really, really cool. Okay? All right, so as you can see that your model is pretty much not that confident in your answer. Okay? But we'll calculate the accuracy right away. I mean, not even calculate. Next, I'm going to show you that the weight value. What is the weight value in your model? So instead of just throwing all the weights, I'm just calculating the norm. The norm is like the magnitude of the weight vectors. Okay, so the norm is this one. So you can see that the norm of the weights is going to change with your C value, as you're going to try it later. Okay, and also I'm going to print the accuracy score. So right now the score is very, very low, right? It's 66% accuracy. So what I want you to do, again, I want you to I want to show you this one. So the decision surface too. Okay. So right now, as you can see that the model decision surface is pretty bad because I guess this region is predicting the class 0, right? I think this is 1 or 0 or 2. I need to look at that label. But again, you can see that this region, there's nothing fall into this one at all. So that means that it's not predicting the right value, right? I want you to take a look at this, right? Look at the weight value and see what happened if you change your Z, the C value, okay? So I want you to, so right now my C value is very, very low. It's 10 to the negative 4. So why don't you change into 10 to the negative 2, 1, 100, and 10,000 and see what happened to your decision surface, to your norm of your weights, and see if it's a better model. Okay, go ahead. And the way you do that, it's very easy. You just come here, and you just do that, and then run. That's it. So from now on, when you say changing hyperparameter, just change this box right here and rerun the whole thing. That's how you do. Okay, and compare the results that you see. Okay. So I'll give you a couple of minutes to do, and I'll show you the results too. Okay, so I think some of you might notice that if you start increasing the C value, your accuracy increase, right? And by that, you also increase your weight values too. Okay, so right here, I kind of summarize the value of C that you can use. Yeah, I mean, you can use anything, but from my example, and then the norm of the weight. So again, if your C is really small, then your weight is kind of suppressed. So again, it's like you are suppressing the model ability to learn. So that's why the accuracy is so low. But once you let your model learn whatever it wants, right, up to like 10 to the negative 4, then the model can kind of create the right decision boundary. Okay? So I guess you can kind of see that after C equal to 1, you should be able to have the accuracy around 0.97 and so on. It doesn't change, but then the value of your weights actually change inside, okay? And then as you can see that this decision boundary is much more sensible than the first one that we see, right? It's splitting the color quite nicely, okay? Even though there's still one, I guess, misclassification right here, and that's due to the fact that you are dealing with the linear model. You cannot separate all of this perfectly unless you have non-linear model, which we're gonna go through next, okay? So that's kind of the first limitation. Linear model is kind of limited, right? Okay, so next up is support vector machine, SVM. Okay, this one's pretty popular, and the guy who came up with this is still alive. So that's kind of thing about machine learning and AI. Like the founder of anything in here is still alive because it's so new, okay? Everything 5 years old is ancient in the AI world nowadays. Okay, so support vector machine kind of work similar to the one that we are looking at before, but it also throw in the new really cool idea. It's called what? The best separation. So I guess support vector machine also think about if you are going to draw the line between your points, what should be the best line, okay? And in order to show that, I'm gonna give some toy example here. So let's say you have the data that are separated into two classes, the blue and the red, and you have the line, okay? So imagine that if you draw the line right there, like here, on the right side of the line, you're gonna predict red class. On the left side of the line, you're gonna predict the blue class. So that's why I color the side with the corresponding colors, okay? So if you are perceptron or even logistic regressions, the way that you do, you're gonna draw this line. Makes sense, right? Because here is blue, here is red. Perfect, right? But then, what about if I draw this line? It's still giving me the same result, the same accuracy, because this is blue, this is red, right? I can also draw this line too. Same accuracy. This is blue, this is red. But for support vector machine come up with another concept because it wants me to draw this line only. It was saying that this line is actually better than this line or this line. No, not this line, but this line. This line is the best. And how does it, but think about this. If you think about it intuitively, I think you will agree that the middle line is the best line. Even though all of this line give me 100% accuracy, the middle one is the best one, okay? Let me show you this, okay? I kind of told you already that this one is better, right? But why this one better than this one, okay? The reason is that, let's say I have another new point. This is a new point that I don't know the class. I don't know the answer. I just know the x coordinates, right? If I were to use this model right here, this model will give me the prediction that this green point is in the class red because it's on the right side of the line. But this model will give the prediction that this green point is in the class blue because it's on the left side of the line, right? Now, what do you think? If I don't know what the ground truth class for this point, what do you think is the most sensible answer, right? So, proximity is the only thing that we have, right? This point is closer to the blue. Proximity, so it makes more sense for this point to be blue, right? So that means that even if I don't have any more information, then proximity is probably our best bet for prediction. So this model is actually better because it gives the prediction of this one that will be kind of based on proximity rather than this one, which gives me, I guess, not the right answer in the proximity sense. Okay? So that's just a concept of what the best separation line is. And this feature is not available in perceptron or logistic regressions. Okay? So how do we encode this one in terms of equation, right? You gotta input this concept in your optimization algorithm. And again, if you want, you can go through my detailed slides. I talked about it in detail. But in a shorter way, it's about margin. Okay? Margin is something like this. If you were to draw a line that's separate between different class, the margin is the distance between your line and the closest sample of that class. Okay, so for example, this would be my, I guess, my margin from my line to my blue class, right? And this would be kind of like the margin from my dividing line to the red class, okay? And the thing that I want to do in order to come up with my best line is I want to maximize my margin. That is your optimization problem right here. So now in support vector machine, your optimization, target, or what is the term for that? The objective function, yeah. The objective function is to, first, you want to minimize the error. That's the same thing for logistic regression and for perceptron. But you have another objective function is to maximize the margin. So you can minimize the error while maximizing the best line possible. So I think that is a very, very cool concept for support vector machine. And this is my favorite algorithm to use for nonlinear model because it's so fast and it's actually do the job really, really well. Okay, so what's the parameter that you can use for a support vector machine? First, again, C, okay? Same thing, C is your suppressions. If you suppress the model too much, you're gonna make the model more stupid, but it's gonna be less sensitive to noise. Sometimes you might wanna suppress your model a little bit, okay? So that it doesn't go wild. You can say that if you smaller C, allow more misclassification. The name, it's soft margin, okay? But I don't think you need to be concerned with that because you need to know a lot more about margin. But again, C, smaller C can be more stupid, okay? I guess that's my tagline, okay? Larger C, okay? I guess it will be, better model, but it can be a little bit more noisy too, okay? All right, so we're going to use that concept and we're going to go through exercise of just coding this. Again, you don't have to change anything much except for the class definition and some of this value, okay? So right now, I'm gonna leave this word kind of vague for now, but we're going to use the kernel that are linear. Okay, I will tell you this more once we finish this exercise, what the kernel is. But right now, we're going to use the linear kernel. Okay, and let's see what the value of weight and then what's the boundary is going to be. Okay, let's go. Here, we're going to move on to SVM. I'm going to close this. I don't need this one anymore. And this one, and then this one. Okay. I'm going to do c1.ipynb. Oh, not this one. Okay, first I'm going to load my utility functions. As you can see that things are getting pretty much identical, like almost identical to the first code. So you're going to, I think you're going to feel more comfortable using this from now on because it's going to get more repetitive. Okay, so the only thing that that's different from your previous code is we are loading something else. sklearn.svm, we're going to import support vector classifier. So I guess the real name is support vector classifier, not support vector machine. So the support vector machine consists of support vector classifier and support vector regressor, which is going to be from after the midterm. Okay, so same deal. Oh, I don't have util. What happened? Okay, got it. So load the data, right? Same thing. And I'm going to extract the two columns and extract the y. Go. Okay. Next, I'm going to split things in 70-30% stratify manner. Random state equal to 1, like that. And then I'm going to do standardizations, like that. Go. Okay. And here's the thing. Oh, okay. So here's the thing. This is a new way of doing things because sometimes you're gonna find that you're gonna have to keep changing things a lot. So, but let me just do my first iteration with just coding everything in terms of just a variable first, just to show you guys, okay? But you can just click enter, but I'm gonna kind of simplify things for you. So I'm gonna say kernel equal kernel, okay? Sorry, kernel equal linear, sorry. And I'm gonna do C equal 0.01. So if it were before, this is what we're gonna do, right? But you have something a little bit more complicated, but essentially we're doing the same thing right now, okay? Okay, so what I'm gonna do next is that I'm gonna do SVC, which is the new class definition that we load, right? We are going to do kernel equal kernel, because kernel is the argument, right? And then the value, and then C equal to C. I think that's it. Do I want to do anything else? I don't think so. Okay. Oh, I want to do random state and verbose, so let me just do that. Like that. Okay. So this is identical to your code. Your code is a bit more complicated. I will come back later. Okay. This is identical. Guess I need to run it. Yep, I run it. And next, I'm gonna do. Okay, I guess I need to put this into a variable called SVM, like that. Okay. So SVM. Now I'm gonna train it, fitting it. Right? Fitting is solving the optimization problem. Okay, fit with X train and Y train. Okay, like that. Done. Okay. And I'm gonna predict. Let's say if I have something else. Yeah, I don't even have anything. I just predict things. So I'm gonna do Y predict equal SVM dot predict. I'm gonna do X test STD. I got my prediction, okay? And this one, I guess you can kind of skip it. I just want to show you the one that I just summation of the flower that get wrong predictions. But actually, I can even just do this. I can even just skip to my prediction scores, okay? And then I'm going to go through this printing a little bit so that I can show you, I guess I do need this summation of misclassified sample. So let me just do that right now. Okay. Rerun it. Okay. And here I have the results that says that for this type of settings, I misclassify 30 example, which means that my accuracy score is so low. And that's exactly because of my Z values. Okay. All right. So before we go further, I want to show you what I did in terms of because my code is a little bit more complicated, but that's something that you can use when you are doing the exam, because you're going to be changing things a lot. So let me show you this trick. Okay. So first of all, I know that I'm going to change this kernel and Z value multiple times, right? So I want to keep this thing a little bit more kind of like programmatics, right? So the way that I do is that I want to have a lot of experiments, right? So for example, I want to keep things in a collection. So I'm going to say parameter set, okay? It will become a dictionary, okay? So again, when I keep things in dictionary, that means that I can keep multiple sets of things, right? For example, I want to do my experiment 1. It has to be a key, right? My experiment 1 is another dictionary, right? And this dictionary has the name, the key, which is kernel, right? Which is linear. And also it has another key called C, which is 0.01, okay? So if I define things like this, if I want to extract this dictionary, right, I need to know the key. For example, if I were to do param set of ex1, then I get the dictionary. So that's exactly what I'm doing. So I'm saying that my parameter, right, param, equal to the key. So that is the experiment that I want to do, okay? So if I were to have what you have, if I were to rewrite what you have right here, let's say my parameter set consists of 3 things. So that means that I can change this to be a different value, right? And if I just first, if I change this one to ex2, that means that I have a new value from my, param set, right? Param, okay? That means that I can control multiple things, like this, right? If I change this one into number 3, then I can change my C value. As you can imagine that, for example, in your midterm, you're going to be changing a lot of things. For example, like maybe in one model, you might want to change 5 things. And if you have to keep like writing things and keep changing things in your code, that's too tedious. That's why I suggest that you maybe group things in the experiment way. So this experiment, there's going to be 5 things that I use. The next experiment, there's going to be another 5 things that I use. And you can kind of get that value by just keep changing just the one, the param right here. So that's how I would suggest that you think about the way that you like experiment with things, like so that you don't have to keep typing a lot of value, okay? And once you have this thing, the cool trick of this is that you can kind of put this into your constructor right here by just using what's it called, the destructuring also. I can do this param set, right? Remember that param set with param is actually a dictionary, right? But I want to kind of expand this into, so let me just do this, okay? I want to do similar things to what I did here, but I want to do it in a more programmatic way, so I can do this. I'm going to delete this. I'm going to do param set, okay, with the param value. But then I'm going to expand it out. So I'm going to do the double star, okay. I never show you this before, but this is a very nice way. If you want to input a lot of keyword arguments into your function, just use dictionary first and then expand the dictionary out into your function arguments. So you probably have to wrap your head around this one because there's no better way to just saying that it works. I mean, for me, when I learned this, I'm just kind of have to trust myself that it works, and it works every time. But kind of convince yourself that when you have a dictionary and then you expand, this is called destructure. With destructure with the double star, it's as if you were doing this one, meaning that you are going to write the key equal to the value. That's what it's doing. So I'm going to use this one a lot from now on because this allows me to kind of construct my parameter and just throw it into my constructor like this. It's such a concise and short way to do. So get used to this, okay? So we're going to use this one from now on. So convince yourself that this one is the same as what I just write in my comments above. Okay, convince yourself, okay? All right, so after you do this, I think I should show you my decision surface, right? What happened? Let's do just that, okay? So in order to do that, I'm just gonna run my code again, and just, where's my code? Here, there you go. Okay, as you can see that if your C is too small, if you are separating things too much, so it's stupid. You see why it's stupid? It's draw the line right here. This is so stupid, man. You gotta make it smarter by controlling it less. Okay, so why don't you help me increasing the C value and see what happened to the decision surface and also the accuracy. Okay? And now you can do things by just changing the value of this param right here, the EX. Yeah, change this one and rerun it and see what happened. Shall we? When the C value is higher, maybe I'll just do 100. So I'm going to go to exercise 3, EX3, right? And rerun it. And as you can see right away, what? Still the same, something wrong. Do something wrong here. Oh, you know why? big mistakes here. Standard. Yeah. So even I do make mistakes. Okay. And it's a very, very easy mistake to make. Okay. So be very careful. Okay. That's why it's so bad. Yeah. That's what I was expecting, right? So maybe I should go back again and do the first exercise. Maybe my first exercise should not be that bad because I don't use the standardized value. Okay, so actually it's not that bad. Okay, so sorry guys, I made some mistake. Okay, so as you can see, when your C is small, it was doing okay thing. But did you notice this line, for example? This is not the best line. The best line is the line that divides the class with the margin that is maximized. This margin is not maximized at all, right? If you want to maximize the margin, I mean that you have to maximize the margin to both classes. This one is not maximize the margin to the orange class, okay? So if you let the model do its thing by increasing the C value, you should be able to see that your decision surface is actually better. It's actually go into the middle. So I'm going to increase my C to 100. And you should be able to see that, here you go. There you go. Perfect. Okay. So that's why I like SVM, because it actually do more than just draw a straight line for me. It's do the best, I guess, best possible way based on proximity to. It will give me pretty much a pretty good prediction as long as your class is clustered together. Okay. Okay, let's move on a little bit more. Okay, so I was telling you that, so these are the, so as you can see from my different animation that the decision surface kind of changed based on the value of C, right? Okay, but as you can see that this is still linear model, right? It's not better than, it's not much better than what we had before. And you are absolutely right because of the kernel. As you recall, we set the kernel to be linear, right? But SVM actually has a better trick on its sleeve because you can set the kernel to be something else, okay? And this is a very, very cool thing that SVM allows you to do. For example, if you are using the linear kernel, you essentially drawing a line, linear line, in the, I guess, in the current space, right? Current dimensional space, okay? But in SVM, you can use another kernel that allows you to kind of transport your data into a higher dimensional space, and you draw the linear line in that higher dimensional space, and then you transport everything back into your normal space, and it becomes non-linear. So SVM is a linear model, but it doesn't restrict you to the only dimension that you have. It allows you to warp your data to a higher dimensional space and then come back to your normal space, and then your decision surface will become non-linear. So that is the power of SVM. So essentially, it's called projection of data into higher dimensional space. So now you can draw any complex shape that you want, but in the end, it's still linear model. But the ability to warp into another dimensional space is really cool. Okay. So and the choice of that high dimensional space is the kernel. Okay. All right. So what are the types that you can do? Okay. First, if you do linear model, this is no conversion, no projection at all. But you can choose a polynomial space. So that means that you can have the polynomial with the degree of d. So the more d that you have, the higher d. That means you are using a higher dimensional space in the polynomial projection. Okay? But this is not even the famous one. The most used kernel is called the Gaussian kernel. So this one is really cool because this one is infinite dimensional space. So you actually project your data into the infinite dimensional space, and then project your data back once you draw the decision surface in that the infinite space. So it's almost like mind bending stuff. Like you are drawing your straight line in the infinite dimensional space. I think that's really cool. So essentially, this allows you to be really, really nonlinear, and you can see that here. Okay, so I'm not even going to go into the details because it's quite complicated and mathematic heavy. But essentially, the kernel works like this. It's an exponential function that tells you kind of like how things are similar. I guess that's the best way I can describe, right? But the way that you do is that you're going to have to specify this parameter right here called gamma. So I guess the best explanation I can come up is a cutoff value for Gaussian sphere. But it has a very, I guess, theoretical meaning. So if you want to understand more, you got to dig into the equation. But essentially, if you want to think about it right now, it's more like the influence of your decisions of your decision surface, for example. That's the best I can come up with. But essentially, I want you to try with this value and see what it does to your decision surface. Okay? All right, so we are going to use just like that. Okay? So we're going to use this. So we're going to use the C value. Again, the C value control how much you want to suppress your model. But then you're also going to vary the gamma. And the gamma kind of affects how much your data are influencing one another in terms of the nonlinearity. Okay, so let's do that, shall we? Again, I'm going to go to my code, and I'm going to quickly kind of copy things for you, so that you can see that you don't have to change anything again. Okay, and actually even cooler. Okay, the code is actually similar up to this point. Like I don't even have to use a new code. I can just come up with the same code. I'm going to copy it, right? So this one, the same code. Okay. And the only thing I need to change from the previous code is actually I have to change this one, kernel to RBF. So it's called radial basis function. That's a Gaussian kernel. That's all. See how easy it is? I have to change this one, and I'm done. But then if I want to do gamma, I gotta write gamma. So I think it's called gamma, if I'm not mistaken. Yeah, it's called gamma. So I just need to say gamma, right? And just equal to whatever value you want, 0.1 or whatever. So right now you can see the benefit of writing things like this, because if you're changing two things at a time, it's become harder for you to keep changing the value in your code. But it's more convenient if you kind of put things like this, right? You can do maybe, I want to do this one, right? I want to create a lot of experiments like that, right? Maybe 4 of them. 1, 2, 3, 4. And you decide beforehand what you want to change. So for example, I want to keep C the same. I want to change gamma from 1 to 10 to 100, right? To 1,000 to 10,000, like that, right? And, sorry, this one's the same, right? So 2, 3, 4, 5, right? And let's say I want to change my C, but I want to keep my gamma the same. All I need to do, I'm just copy everything, right? And then I'm going to say, okay, my gamma is actually going to be 0.1. So I kind of specify things beforehand, 0.1, 0.1, 0.1, right? But now I want to change C from 0.01, right, to 0.1, to 1, to 10, and to 100. And the nice thing about this is that you know what you want beforehand, and you can kind of, because everything is written in your code. So then when you come back again, you know that these are the things that I experiment with, instead of just changing things in your code, and then when you get saved, it's gone. This one, you know that there are 10 experiments. The one that you're choosing is experiment number 7, like that, and you just run it. So I do recommend thinking about, when you are experimenting like in the midterm, that you write something in your code on what you want to do, and you select what you want to do from your code. It's better than just code in the value itself, okay? So that's another trick that I find most very useful, okay? So right now, it's not doing it because I don't have this thing anymore. Because if it's nonlinear model, I don't have coefficient, I think. So I gotta uncomment this one. But you can use my code. It should be correct. Yeah, that's what it is. Okay. So I want you to keep changing the value of C and gamma to see what happened to your code. Okay. Okay. And as you increase your gamma, you're going to find that you can have something as nonlinear as like this, which is so cool, right? So something like this cannot be done with the linear model. But SVM is kind of like special linear model that can transform into higher dimension. So it can also do nonlinear stuff, just even like that. Like I really like, this one is probably the one that you want to go to if you need something nonlinear. Really good, okay? Okay, and if you want to see more example, I also get the example for you. And this one is a toy data. It's called the XOR data, okay? And I also have the code in your folder. But as you can see that if you increase gamma, then you can make your decision surface like more and more wiggle. Like, and even it can do its own island like this. It's so cool, right? So this data is very difficult for linear model to do because there's no way you can divide your color with the linear model. And it also has like separate islands like this. But SVM can handle that beautifully. So that's a good thing about SVM, right? And also, if you increase the C value, then as you can see that this one model is very stupid. That means that it's going to do a lot of misclassification because you suppress it too much. But this one, you can see that it's kind of go along the separation line between the two classes very well, right? So I guess the bottom line for the SVM is that, or any like logistic model and SVM is that you want to try higher C first. You don't want to suppress your model too much. If you don't have noise problem, then let it learn. You know, do not suppress it, right? And also for SVM, you also have gamma that you can use to kind of increase your, I guess the non-linearity of your model. But do not do it too much because if you did too much, you might end up with something really weird like this. I will show you. If I increase gamma too much, maybe exercise 5. Okay, so this one is 10,000. Then your model is going to break like this. So yeah, too. So gamma, it's something that you might want to do too. And again, you don't have the luxury of seeing something like this, but you can see right away that your accuracy is pretty bad. So that's something you can detect too. Okay. I guess due to the interest of time, I do have 3 more models for you. But I guess I probably better off just recording a video for you to take a look before the midterm. Because at least if we finish this one, then I guess that's a good place for me to actually give you the midterm. Like without the rest of the model, then the midterm doesn't make any sense. So let me record the rest of the material, which is probably going to take like less than an hour, I think. and then you can watch it on your convenient time. And the midterm is going to cover until from the starting of the class until the video that I give you. Okay, and again, it's going to be take home, spend a week on it. But I don't expect you to spend literally week on it. You should take you like a couple hours to do. But because it's Python, so you might want to maybe take your time and kind of explore how you can do things in your code. Because when you write things from scratch, it takes some time because you make lots of mistakes and it's going to get things. So I want to give you more time on that, okay? All right, so Happy New Year. See you next time after midterm, all right? After midterm. It's going to get more fun after this.